Hi, this is Jana Ibrahim's video series on Bipolar Junction Transistor or BJT. One of the main building blocks of modern electronic circuitry is the transistor. It is a three-terminal device of which its output current, voltage and power are controlled by its input. The transistor is often used as a primary component in the amplifier, that is a circuit designed to increase the strength of an input signal. It is also used in digital switching application, particularly high-speed switch that control between two operating states, open and close at a rate of several billion times per second. There are two types of transistor, the Bipolar Junction Transistor or BJT and the Field Effect Transistor or FET. These two transistors differ in the operation characteristic and internal construction. In this video, we will take a look at the BJT. The Bipolar Junction Transistor or BJT has three terminals, namely emitter, collector and base, and made up of semiconductor materials. There are two types of BJT, NPN and PNP. For the NPN type, the emitter and collector are made of N-type material, while the base is from a P-type material. On the other hand, the Pnp-Bjt is constructed in the opposite manner. The emitter and collector are from P-type material with N-type base. Here is the BJT schematic symbol. Note that the arrow on the symbol is representing the emitter terminal. Hence, the terminal opposite the emitter is the collector and the center terminal is the base. The arrow always pointing towards the N-type material, which means if the arrow is pointing towards emitter, it is a NPN-Bjt, and if the arrow is pointing to the base, it is a Pnp-Bjt. There are three currents in BJT. IE is the emitter current, IB is the base current, and IC is the collector current. In general, the IE has the greatest current value than the other currents. The current's direction in a NPN-Bjt are the opposite of those in PNP. BJT is a current control device, and in normal condition, the values of IE and IC vary directly with the value of IB, which means an increase or decrease in the value of IB will cause similar changes in IC and IE. The IC value is the value of IB multiplied with the forward current gain or beta. Therefore, IC is equal to beta times IB. For example, if given IB is 60 microampere and beta is 100, we can find IC by multiplying beta and IB, and it is equal to 6 milliampere. There are many voltages related to BJT. A simple way to remember voltage is when the voltage has a double script such as VBB, VCC, it means it is supply voltage, and VCE, VBE and VCB means it's the voltage between the terminals. Note that voltages are measured across two terminals. So for VCE, it means between collector and emitter terminals. When only one subscript is shown, the voltage is measured between the terminal and ground. The BJT is made up of three separate materials, which create two PN junctions as shown. The two junctions, namely the base emitter junction and the collector base junction. From previous discussion on diode, when NPN-Bjt is not biased, the unbiased PN junction forms a depletion layer at room temperature. When base emitter junction and collector base junction are both reverse bias, the BJT is in cutoff region. When base emitter junction and collector base junction are both forward bias, DBJT is in saturation region. The active region of DBJT is when base emitter is forward bias and base collector in reverse bias respectively. When both PN junctions, BE and CB, are reverse bias, the two depletion layers extend well into the emitter, base and collector regions. Larger depletion layers mean only an extremely small amount of reverse current can pass from the emitter to collector. In other words, IC is nearly zero. The opposite of cutoff is saturation. This happens when BE and CB are both forward biased. But the increase in IB does not result in the increases of IC because it's already reached its maximum possible value. For example, let's assume that the VCE for saturated transistor is 0 volt. Hence, IC will solely depend on VCC and RC and RE. And IC reached its max value. Hence, any increment in IB will not reflect to IC anymore, and the IC equal to beta IB will no longer true. Here, the IC reaches its maximum value. The active region occurs when BE is forward biased and CB is reverse biased. This region is between the saturation and cutoff regions. When the VBE receives sufficient voltage, PN junction will allow current to flow, and VBB and VCC generate currents in emitter, base and collector regions of BJT. The base terminal is lightly doped, hence its resistance is much greater than that of the reverse bias CB junction. Therefore, most of IE comes from the collector via the reverse bias CB junction. In a nutshell, BJT will follow its current and voltage rules when operating in active region. According to the KCL, IE must be equal to the sum of IB and IC. Normally, IB is very much less than IC, hence the IE and IC can be approximately equal. Beta is the ratio of DC collector current to DC base current of BJT. Beta is equal to IC over IB. Beta is very important because most common transistor circuits have an input signal applied to the base and output signal taken from the collector. Thus, beta can represent the overall DC current gain of the BJT circuit. Using the IB and IC relationship and the KCL that relates three BJT currents, we can show that IE equal to beta plus 1 times IB. Note that beta has no unit because it is a ratio and can be up to 300 for BJT. Alpha is the ratio of IC and IE, or alpha is equal to IC over IE. Its value is always less than unity. The reason for this is the KCL states that IE is equal to IB plus IC. Hence, IC will be equal to IE minus IB. And since practically IC is always less than IE, the ratio of IC over IE must be less than 1. Note that alpha is usually 0.9 or higher, and IC is equal to alpha IE. Therefore, we can relate that IB is equal to IE times 1 minus alpha. Let's discuss the relationship between alpha and beta. Beta is a DC parameter that is most commonly used than alpha in BJT calculations. Although alpha is rarely used, we can determine its value by using beta. With the relationship, alpha is equal to beta over beta plus 1. The Pnp-Bjt has the same basic operating characteristic as the Npn-Bjt. The primary differences are found in the polarities of the voltages of the circuitry and the directions of the currents IC, IE, and IB. Here is the summarized operating characteristic of NPN and Pnp-Bjt. And that's our discussion on the introduction of BJT and its operating characteristic.